Okay, everybody. So this is a supplemental video on the analysis of variance. So let's look at ANOVA. So analysis of variance is often just abbreviated ANOVA. And one note, just similar to some of the other topics that we're covering at the end of the course, this can be a much bigger topic to discuss or to talk about. We're covering kind of one specific case, the one-way analysis of variance or single factor analysis of variance. There are other ANOVA tests that could be discussed, but we're just not getting into those. So, maybe a second semester stats course or a stats course geared toward one or another field might cover ANOVA at greater depth, but we're just scratching the surface here to give you an idea of how ANOVA works. So what is the goal of ANOVA? We would like to determine whether the means of several populations, typically 3 or more, are equal. So we have 3 different populations. Maybe we could think of it, for example, as maybe a control group and 2 treatment groups or something. And we want to know, is their mean time to recovery all the same, or do we think that there's at least one mean that is different from the others? And the strategy is kind of counterintuitive. So the name of the procedure is analysis of variance, which makes us think about variance and standard deviation, things like that. But we're trying to answer a question about means. So counterintuitively, we actually use information about variances to make inferences about the means. This seems like a very strange thing, but in a minute here, I think the reason that we do this way will make a little more sense. For convenience of notation and writing things out and showing examples, we'll restrict our study to just 3 populations. But these ideas generalize to n populations. You could have 4, 5, 6 populations, but we're going to just stick to 3 populations just for the examples. And so here our hypotheses are, the null is that the means are all the same, mu1 equals mu2 equals mu3, and the alternative hypothesis is that at least one of these means is different from the others. So it could be that mu1 is different, but mu2 and mu3 are the same, or mu2 is different, mu1 and mu3 are the same, mu3 is different, mu1 and mu2 are the same, or that all 3 are different. So there's kind of lots of situations that could pop up as the alternative hypothesis, but the null is that all the means are the same. And the following picture, or I suppose maybe you think of it as 4 pictures, I think is the most important picture in ANOVA. And here's the idea. Let's consider 3 populations. We can find X bar for each of the 3 populations, and these 3 populations are going to have a mean. X bar has some sampling distribution. We have some deviation about the mean, possibly from X bar. We think that the X bars have a normal distribution from the central limit theorem. And if we look at the top left picture here, this might be a picture where we have 3 X bars, X bar 1, 2, and 3 for the 3 different populations, or sorry, for the 3 different samples coming from the 3 different populations. And those X bars are fairly close to one another. They're fairly close together. Their sampling distributions kind of overlap quite a bit. Versus we could think of a situation like the top right, where we have one of the X bars that's quite far away from the other 2. So X bar 1 is quite far away from X bar 2 and X bar 3. X bar 1's distribution really doesn't overlap much with X bar 2 or X bar 3's distribution. So I think just looking at this, we can see that on the top left scenario, the null of the means being the same, mu1 equals mu2 equals mu3, would be a pretty reasonable hypothesis to stick with, right? Getting an X bar 1 that's a little lower, an X bar 2 that's a little higher, that seemingly could have easily occurred by sampling error. But the top right, probably much less likely, right? To get an X bar 1 that was this far away from the X bar 2 and X bar 3 doesn't seem likely to have occurred by sampling error. Okay, so looking at these pictures, that makes sense, but why are we looking at variances? Well, let's consider the variance of the top left versus the top right, or the variances. We could look at sample one and compute kind of a within sample variance. We could do the same for sample two and sample three, right? We could get the within group or within sample variances. We could also kind of glob all of the data together, put all of the three groups kind of together into one big data set, and get kind of an overall variance. Now, if we think of the overall variance for, say, the top left picture, the overall variance for all of the groups kind of combined together into one big data set is probably going to look more or less like the variance for any of the individual groups sample data. But if we look at the right over here, and this is the really key observation, is that we have some contribution to the variance from just sampling error within the groups. So in other words, X bar one might be a little far away from U1 just by chance, just by sampling error. There's going to be some variance there, some for the second, some for the third group. That's what we might call SSE, the sum of squares due to error, or the kind of the variance due to sampling error. But then we note that X bar one, kind of its whole distribution is really far away from X bar two and X bar three, or population one or sample one is kind of really far away from sample two or sample three from their typical data. So when we glob all of the three groups together into one big data set, kind of relative to groups two and three, relative to the members of that big combined data set that come from populations two or three, all of the folks in population one kind of look like outliers. And remember that outliers disproportionately affect variances. So in other words, my top right kind of overall variance is going to be like much, much larger than my within group variances, than my variance for sample one or sample two or sample three. But we don't see that in the top left. The kind of between group variation is going to be quite small. It's going to be a quite small contribution to the overall variance when everything's combined together. And the overall variance is probably going to look more or less like the within group variances, one, two, or three. Or another way that we could visualize this is to draw box and whisker plots. On the left side here, we have a box and whisker plot where a good portion of all of the boxes kind of overlaps with each other. There's a pretty decent range in here where all of the boxes even are overlapping with one another, to say nothing of the whiskers. But if we look at the right scenario here, and I try to draw these fairly accurately, if we look at the right scenario here, well, the red and green box overlap one another quite well, but the blue box is kind of completely separated from the red and green boxes. It's only the ends of their whiskers that overlap between the blue, green, and red. So once again, outliers in a data set contribute disproportionately to variance. They disproportionately increase variance. On the left side, or on the top left example, relative to population one, the data from populations two and three don't really seem to be outliers. The same could be said for population two's perspective of one and three, or three's perspective of one and two. Nobody really sees the others as outliers. But on the top right picture, from the perspectives of samples or populations two and three, basically all of the data from sample one, or the result in X bar one, basically all of that data looks like an outlier to samples two and three. So when we put all of the data together and compute a variance on the top right, that variance for the combined data is going to be much larger than the variances for the individual samples, where on the top left, the variance for the overall data is probably going to be about the same as the variance for any of the individual samples. So this is why we can analyze variances. We can say if I see a situation in the variances where the overall variance is much, much larger than the kind of individual sample variances, the within group variances, that's an indication that at least one of the means is not the same as the others, or that there's some data within one of these groups that the other groups are kind of seeing all of that data as outliers, in a manner of speaking. Okay, so just to summarize, as I mentioned, on the right, from the perspective of populations 2 and 3, essentially all of the population 1 points are outliers, which dramatically increases the variance. A little bit of terminology. So unfortunately, ANOVA is, well, I suppose not unfortunately for this, but ANOVA is a very important method that's used across a lot of fields, but unfortunately being used across a lot of fields means that kind of each field uses terminology or wording that that kind of fits their field a little better. And unfortunately, they also use abbreviations that fit their fields maybe a little bit better, that fit that terminology better. And we get a little bit of overlap in the abbreviations, unfortunately. So the same abbreviation in different contexts might mean different things. But usually if you take the context as a whole, you can tell what's going on. So the populations, these different groups, sometimes they're called groups, sometimes they're called treatments. You know, if you're maybe in more of a medical field, sometimes they're called factors. So factors that can influence something. I hear that a little more maybe in like the psychology field, something like that. But that's certainly not an exhaustive list of who uses what wording. We have the idea of the total sum of squares. This would be if we take all of our samples, combine them together into kind of one big sample, and take that data set and compute what is essentially a variance. So this is the total sum of squares, which I'm denoting SS for sum of squares, or which some folks sometimes denote SST for sum of squares total. There's the within group or within treatment sum of squares. So within each sample, there's a sum of squares. The sum of squares of each subpopulation sample or each group's sample. And we call that SSE for sum of squares due to error, or in other words, due to sampling error. There's always going to be some variation just due to sampling error, even if the means are the same. And then we have the between treatment sum of squares. That is this big deviation up here. That's the contribution to the sum of squares from, say, x bar 1 being far away from x bar 2 and x bar 3, x bar 1 looking like an outlier relative to sample data 2 and 3. The between treatment sum of squares is called SST for sum of squares due to differences in treatments or differences in the means. Sometimes this is called SSTR. So we either have SS related to SSE and SST, or we have SST related to SSE and SSTR. So you look for the difference between, do you have SS or SSTR? So here we have sum of squares equals, so the total sum of squares equals sum of squares due to sampling error, the within group sum of squares, plus sum of squares due to treatment differences, the kind of between group sum of squares. And the variation can actually be broken down this way. So we're not going to go through the details to show this, but we could break the total sum of squares into these two components, those due to sampling error and those due to the means being different, or at least the x bars being different. And roughly speaking, if the sum of the squares from the treatment differences, the between group sum of squares, is much larger than the sum of the squares within the groups just due to sampling error, we think that suggests there's a substantial contribution to the overall variation from the difference between treatments, from the difference between the means, suggesting the means are not the same and we should reject H0. If the total sum of squares basically looks like sum of squares due to error, due to just the sampling error, the within group sum of squares. We think that probably most of the overall variation is just due to that sampling error, and there's just a minimal contribution from the difference in the means. So we probably ought not reject H naught. We probably ought not reject the hypothesis that the means are all the same. So let's consider a sample statistic. We call this one F observed. So sometimes we had like a Z observed for a Z distribution or a T observed for a T distribution. Well, we construct a sample statistic that's SST over SSE. That's the sum of the squares between treatments over sum of the squares due to sampling error. And we call this distribution F. We say that this sample statistic is distributed with a distribution called the F distribution. So it's kind of like a normal distribution or a chi-squared distribution. It's just a different distribution we haven't talked about yet. Now, because these are sums of squares, this is always positive. Because we're adding up squares of things both on the top and the bottom, we have positive or positive, that makes a positive number. And remember what we said, that if sum of squares between treatments, sum of the squares due to the treatment differences, is much larger than the sum of the squares due to just sampling error, we want to reject H naught. If SST is much bigger than SSE, that means F observed is a very large positive number. So if F observed is large, we reject the null. Otherwise, we fail to reject. So this is a right tail test. So what I would like to do is to compute F observed to find an F critical, and then say if F observed is larger than F critical, I reject. I reject the null. I conclude that at least one mean is different than the others. And if F observed is not greater than F critical, then I don't reject the null, and I conclude that the means are the same. So what is the sampling distribution of F? So F observed we can write as, again, this was kind of a rough equals here, but really it's SST over something we call nu1, the Greek letter nu, the Greek letter n, over SSE over nu2. Sometimes this is called something like the mean square due to treatment over the mean squared error. And here, nu1 is the number of treatments or the number of groups minus 1. This is usually called the numerator degrees of freedom. And nu2 is the total sample size minus the number of treatments. And it's the denominator degrees of freedom. And F observed, which is this ratio, is basically the ratio of two standard deviations or two variances. And we know that kind of roughly speaking, variances are distributed according to chi-squareds. So it turns out that the F distribution is just a ratio of chi-squared numbers. So the F distribution, again, has 2 degrees of freedom, typically referred to as numerator degrees of freedom and denominator degrees of freedom, nu1 and nu2. And as a ratio of chi-squareds, it actually looks kind of like the chi-squared. It is a non-negative distribution, again, because of this. And it's right skewed. So it actually kind of, the rough shape of it looks more or less like a chi-square distribution. Okay, couple of side notes. The first side note, what if the number of treatments is 2 or the number of groups is 2? Well, we can imagine then that the hypotheses are just the null is mu1 equals mu2. The alternative is mu1 not equal to mu2. So I suppose we could use ANOVA, but we also saw hypotheses like this in chapter 9, just testing for the difference between two means. We have two different ways of running the same hypothesis test. Is this bad? Is this problematic? What if one of the ways says to reject and the other way doesn't? How do we decide? Well, it turns out that they're exactly the same test, right? The details might be slightly different, but they will always either both result in a rejection or both not a rejection. Why is that? Well, F observed again is this ratio of chi-squareds. But here where we have two groups or two treatments, nu1, number of treatments minus 1 is just 1, and nu2 is n minus 1. So for these two treatments, F is just chi-squared with 1 degree of freedom over chi-squared with n minus 1 degrees of freedom. A chi-squared with 1 degree of freedom, remember we get chi-squareds by adding up z-squareds, and chi-squared with k degrees of freedom, we add up k z-squareds, z1 squared plus z2 squared out through zk squared. So a chi-squared with 1 degree of freedom really is just the square of a standard normal divided by a chi-squared with n minus 1 degrees of freedom. And it turns out that this thing, z over root chi-squared n minus 1, that's actually what the t-distribution is. We didn't really talk about those details, but it turns out that F, in the case of two groups, very important, in the case of two groups where the numerator degree of freedom is 1, in that case, it turns out that F is just t squared. So it turns out that these are two completely equivalent ways to approach the same topic. Now, we might say, so therefore, this idea of ANOVA and the F distribution and all of that is just a generalization of the t-test. But after seeing this, we might say, well, we know how to do t-tests. Why not just, instead of testing for all the means at once, why not do a t-test for mu1 versus mu2, one for mu1 versus mu3, and another for mu2 versus mu3? Couldn't we do this? Couldn't we just see if any of these generate a rejection? And if they do, then I know that at least one of the means is not the same as the others. The issue we get here is that if we, say, perform this first test with alpha of 5%, and then do the second test with the same alpha and the third with the same alpha, we might think that we're controlling the type 1 error to be less than 5%. But the problem is that really, if any of the three tests would generate a rejection, then we have an overall rejection. But basically, this one or this one or this one could generate a rejection. That's like 5% chance for each of them, or 15% total chance. My type 1 error would be close to 15%. It's really a little bit different, but my type 1 error would be, say, near 15%, and certainly not no longer controlled at 5%. And the more treatments, the more groups that we compare, the worse this gets. The thing with ANOVA is that by doing kind of everything at once, we can keep the type 1 error rate controlled at 5% and not have to worry about all of this here kind of getting out of hand. So we really do want to assess all of the means at the same time instead of doing something like this. Okay, so in practice, doing all of these calculations by hand would be pretty terrible. So we typically go to Excel and we have Excel do the calculations for us, and it usually pumps out a table that looks kind of like this. So there's the source of the variation between groups versus within groups, and then total. The degrees of freedom are nu1, nu2, or the sum of the two. These mean square errors are the SST, the between group, or the due to treatment sum of squares, versus within group, or due to sampling error sum of squares, divided by their respective degrees of freedom. F observed then is the ratio of these two mean squares, MST over MSE. We can compute a p-value, the probability that the F distribution is bigger than this F observed number. We could maybe look that up off a table or something, but we're going to use Excel for that. And we could also compute an F critical and compare F observed to F critical. Remember, it's a right tail test, so see if F observed is bigger than F critical, in which case we generate a rejection, otherwise we would not. And again, F critical, we could look it up off a table, but we're going to use Excel for that. So let's suppose that we got partially filled in table. Can we use these formulas above to fill in the rest of the table? Okay, so I have some sum of squares and my mean squares. Well, I don't know what my treatment degrees of freedom is, but I do know that MST equals SST over nu1. Or in other words, nu1 equals SST over MST, or that's 1.224 over 0.612. And that is 2. I know that my total degrees of freedom is 2 plus 23 is 25. And what else do I need here? Well, I know my F observed from up here is MST over MSE. So I could try to find this number, MSE. MSE is MST over F observed. And let me switch my share here. So I have my calculator brought out. So what is MST? That's 0.612 divided by F observed is 0.77. And that gives me about 0.795. Make sure I'm in the, yeah, MSE, 0.795. And what else would I want? Maybe SSE. And I know SSE over nu2 is MSE. But I know that nu2 is 23, and I know what MSE is, so SSE is nu2 times MSE. Or that's going to be 23 times 0.795. Or that would be about 18.23 or 29. 18.29 or so. And then lastly, I want to compute my p-value and F critical. So for my p-value, remember that's the probability, the F distribution with these degrees of freedom is bigger than, in this case, 0.77. So I want equals F dot dist, so the F distribution. Now the default is left-tailed, but I see that there's a .rt option for the right tail. F distribution, right tail area. What's my F index? My F observed is 0.77. My numerator degrees of freedom, nu1, is 2. And my denominator is 23. And I see this gives me about 47%. I can compute F critical. Here I want F inverse. So I want to give an area and have it give me an F index for F critical. Again, I want right-tailed, so I'll use the .rt option here. And we're using alpha as 5%. That's just kind of the standard we're choosing to use here. You could use 1 or 10% or some other percent, but we're using 0.05 for the area for the probability. Numerator degrees of freedom are 2, denominator are 23. And this gives me 3.42. And now I see, should I reject the null? I see that I should not. Let me just erase this here. No, and I see that for 2 reasons. On one hand, my p-value, 47%, is much bigger than 5%, which is alpha. Since p, my type 1 error rate, if I made a rejection based on this sample, would be much larger than the maximum allowable type 1 error rate, I do not reject. And I also note, that this would be sufficient information to not reject, but I could also say that because this is a right-tail test, an F observed of 0.77 is not to the right of 3.42, or F critical. For that reason also, I could say do not reject. All right, let's look at a couple examples in Excel. So here we have 2 examples. The first example is on measuring elasticity in plastic produced by 2 different processes. So we have process A and process B with their samples. And example 2 is students being assigned randomly to 3 different teaching methods, and say the students' exam scores or something like that, their results under each of the 3 methods. So just as kind of a warm-up, let's do a t-test here. So we want to know whether there's a difference between the means. So I have x bar 1, I have x bar 2, and I can compute t observed, the difference between the x bar observed over this kind of complicated, annoying, square root thing. And we saw that calculation before. That gives me negative 1.69. T critical, this is a 2-tail test. The means are different if the mean for A is less than the mean for B or bigger than the mean for B. So this is a 2-tail test, area 5% total, and in this case, 10 degrees of freedom. So we have a T critical of 2.23. Keep in mind, because it's a 2-tail test, that's plus or minus 2.23. Negative 1.69 is not less than negative 2.23. Therefore, we do not generate a rejection. We cannot conclude that the means are different. Now, if I wanted to take the ANOVA approach, I would go up to my banner up here and go to the data tab and then data analysis. And we see at the very top here, there's single factor ANOVA. Don't pick either of the other ANOVAs, the 2 factors, just single factor ANOVA. Hit OK. The input range is the whole data, all of the data that I'm looking at, all of the different groups. And I will include labels, and I'll tell it labels in first row to note that I've included the labels. And these are grouped by columns. So in other words, the first column is one group and the second column is another group, as opposed to being grouped by rows. We use alpha as 5%, and I'll put a new worksheet ply. So when I hit enter, I get this, and it's the same as this one that I've cleaned up a little bit so we can see it a little better. And again, we see that we get these ANOVA results, source of variation between groups versus within groups, and total. The degrees of freedom works just the way we saw it over here. We have the mean squared errors. This is our F observed. Note that this F observed, if we come back here, we had a T observed of negative 1.69. If we square that number, which is what I'm doing here from the previous data, or from the previous sheet, if we square that T number, we see we get exactly the same thing here. We can compute a p-value, or well, Excel computed a p-value for us of 12%. So we would not generate a rejection here. We could also look at F critical. Note that F critical is the square of T critical. We look at F critical and we say F observed is not to the right of F critical. 2.87 is not to the right of 4.96. We do not generate a rejection. So we can see here that the F and T tests really are doing exactly the same thing. But in either case, we conclude that we cannot say that the means between the two different processes result in different elasticity in the plastic they produce. And that also seems like a sensible conclusion when we look at the box plot. When we look at the different teaching methods, these box plots don't look so consistent with the means being the same. Maybe the mean between orange and gray, or method 2 and method 3, maybe those are close to the same, but it certainly seems like blue is kind of a bit different. So again, if I go to data analysis, single factor ANOVA, here I'm going to choose this data with the labels in the first row, alpha 5%, new worksheet ply. That gives me this report, and again, there's one that I've already cleaned up here, just kind of changing the column widths and things like that to make things work a little nicer, or look a little nicer. And again, I see I have my same information that I had over here in the OneNote that we worked through. I note that my F observed of 4.1 is indeed to the right of F critical of 3.88. I note that my p-value is indeed less than 5%. In this case, I would reject the null. In this case, I would reject the null that the means are the same, and I would conclude that at least one mean is different from the others. Now, it's super important to realize that what conclusion I've made here on the basis of this p-value, or on the basis of this F observed versus F critical, is simply that at least one of the means is different from at least one of the others. I mean, at a glance, it kind of seems like mean 1 is not equal to the others, and that mean 2 and mean 3 are maybe equal to one another. But I haven't concluded that. My ANOVA test does not tell me which mean it thinks is different from the others, whether it thinks all the means are different, whether it thinks only one mean is different, or 2 or 3, or it doesn't tell me which mean, it doesn't tell me how many, or it just says, I think that there is at least one that is different from the others. So we could have, we could have mu1 not equal to mu2, but mu2 equal mu3. That's seemingly what we have here at a glance, but we could have the means are all different, or there could be a lot of different options. And especially if we got more than 3 groups, the number of options is going to increase very rapidly. So we can't conclude from the hypothesis test that, say, mu1 is less than mu2 and mu3, and mu2 and mu3 are equal, or something like that. That's too strong a conclusion to make just on the basis of the hypothesis test. But we can conclude that at least one of the means is different from the others. And I think probably a sensible interpretation of that result would be that well, method 1 is probably different from 2 and 3, but I probably wouldn't want to go as far as to make a conclusion about whether mu2 equals mu3 or not. Okay, so again, with ANOVA, we're just really scratching the surface. We're not intending to go deeply into this, but again, I think this picture really is the best way to illustrate what's going on. And hopefully now it makes a little more sense why we use variances to make inferences about whether we think that the means are the same or different.